Yeah, so I have been playing around with NES audio for a little while and streaming it on my Twitch just for fun. My Twitch is there. And I'm going to start by showing a quick demo of what that looks like. See if the link works. Oh, come on. Can I? Oh, right. I was actually... Bear with me a moment. I'm going to open the PDF for real. I knew something was going to go wrong. That's why I put the little cross fingers emoji. It's because, oh yeah, yes, good idea. I was looking into how GitHub renders PDFs just out of curiosity, and they're in a canvas element, so I can't select the text. But I can click on under the image. Ah, there it is. Yep, great, cool. All right, is the sound gonna work? Is the sound gonna? The sound works. Okay, great. Progress. We'll turn it down a little bit. Okay, so this is a program that I made. Okay, well, I'll just mute it. Okay, so this is running on somebody else's NES emulator, which is basically as good as real hardware, right? Yeah, it's a NES ROM that gives you access to all of the registers in the APU, the audio processor. There's only 20 of them. If I just, what was it? Yeah. So there's only 20 of them, and they let you control various aspects of various different audio channels. There's only 5 audio channels. Yeah, I was curious what the registers did, and there were tools already that did something similar to this, but I thought it would be fun to make my own, so I spent a week or two hacking together a NES program that exposes the registers, and you can use a cursor to choose which bit you want to flip, and then flip the bits, and sound happens. It's really fun. And yeah, I learned all about how audio works on the NES. And what's even better is I made it in Rust. Yeah, there we go. I wanted to make sure everyone realized that I made it in Rust. I mean, that's what we're here for, right? Yeah, I'm going to talk today about what it's like to make an NES program in Rust, and yeah, plug my DSL that I use for all of my various NES programs. So here's how I use my tool. So when I say that it's written in Rust, what I really mean is I wrote a program in Rust that when you run it, it creates an NES ROM, which you can then run on a NES emulator. So in this case, yeah, this is an example of how you'd run it. If we get a bit under the hood, the library INES, which is one of my NES libraries, defines this INES struct. INES is the sort of standard for making NES ROMs in files so that you can play them on emulators. And this is what it looks like to define an INES ROM and then generate the binary that you can play in an emulator. And the two relevant bits, yeah. That's right. Are we not in the PDF? We're not even in the, oh gosh, this is the markdown file. GitHub did such a good job of rendering it that it's like we don't even need PDFs anymore. But let's just quickly scoot back to the PDF. Here we go. Very good. Yeah. Oh, come on, more pages. Yep. There we go. Okay, cool. So there's these two sections that we care about here. Character ROM, CHROM, and program ROM. Program ROM. So an NES ROM, the physical object that you put in your physical NES, has two different types of ROM in it. One for the graphics, character ROM, one for code and data, the program ROM. And we'll talk about character ROM first, because it's nice and simple. Here's the character ROM that I used for, well, here's a small section of the character ROM that I used for that program on the left. So you can see the letter A there. This is the A sprite. If you look at just the ones, makes an A shape. And so character ROM is full of data encoded in this way, where you use bits to, there's 2 bits per pixel that select out of a table of colors. And on the right there, I needed a font, right? This program is mostly text. And I didn't want to make my own font, so I went shopping around for different NES ROMs that had text in them, and then I wrote a little tool that pulls out the font. Can anybody tell what game this might be from, just from looking at the other sprites that are in the character ROM? So maybe this one, these little eyes. This is Sesame Street, Big Birds, hide and speak. It's really cool. Like it has a lot of audio data in it too. Like it has a lot of spoken dialogue. It's really impressive. And yeah, what's great about this character ROM? I know I'm going off a bit of a tangent here, but the very first character is a space. That's really important because the character, the video RAM on the NES is initialized to all zeros when it starts up, and part of that RAM is a table of indices into this character ROM table. And if the first sprite is anything but a space, you just get that sprite repeated over and over again, and you have to go and zero it all out. So it's just more convenient to not have to do that if the first character is the space. But I digress. What's more interesting today is to talk about the program ROM. And this is what it looks like. I'll show you what it looks like to write that in Rust. So we start by creating this thing called a block. And this is what we're going to use to low-power assembly program in Rust and then emit a binary in the end. It's sort of separated out into this block because ROMs on the NES only has 32 kilobytes of addressable ROM, and that's not enough for most applications. So what games would typically do, because it's a cartridge system, you can have arbitrary circuitry in the cartridge. So most games would have way more than the 32K of ROM in the cartridge and some mechanism for switching out which like ROM is effectively attached to the pins. So for example, the Sesame Street game, you can see it's got 16 kilobyte ROM banks that it can dynamically switch between at runtime. That's how it fit all that audio data, so Big Bird can talk to you as you play the game. It's great. All right, so start with a block, and then we're going to add some instructions. Don't worry, I'll go into way more detail about this in a sec. And then finally, you can emit a binary and assemble the instructions from an intermediate representation inside the block that knows about things like labels to just binary data that you can put into your NES emulator. Okay, so let's get into what it looks like to write this program. So here's an NES, or a 6502, I should say, that's the processor on the NES, a 6502 assembly program written in Rust using a DSL. This is a simple function as an example. You can see that the assembler lets you define labels and then refer to labels as the address of functions, so you can write functions and call them in an ergonomic way. These are all instructions: ASL, TXA, STA. Some of the instructions have a parameter. This is called an addressing mode. Some of the instructions can be parameterized by how they get their arguments, whether they get it from memory in a particular way or from a register like the accumulator. Okay, we'll look at some more examples of NES Rust code. This is how you put static data into your ROM. Possibly people didn't notice, but in the demo I showed, the cursor that selects the current bit was flashing between dark gray and white. And this is the table of color indices that it cycles between. And so you can just say the literal byte operator, which is a directive to the assembler to just literally put this byte at the next address. And then this is an example of how you might refer to that. So this is code from the function that does the cursor blinking by just indexing into this table. The 6582, I said before, was the processor in the Rust. It's the processor in the NES, but there's a bunch of NES-specific stuff that we're going to want to do regularly, like interface with the graphics chip. So it's convenient to extend this block type to allow more platform-specific functions. I've only ever written NES programs in this language, but there's no reason you couldn't use it to write, say, a Commodore 64 or Apple II program as well, if you understand how to pack those into the appropriate file format for the emulator you'd use for those devices. So yeah, you can use a trait to extend the block type to add platform-specific operators. And probably the most powerful feature is that Rust is now your macro language. So you can use Rust loops, say, to generate code dynamically that makes it a lot more convenient to write programs for the NES. So this is an example of using a Rust for loop to repeatedly generate the same block of code 8 times, but using an offset into, yeah, using the loop counter as part of one of the part of one of the static function part of one of the static operator arguments. And finally, we can take advantage of Rust's type system to catch bugs in our assembly code. So this is an example of an invalid instruction. This is the inc instruction, which increments a value in memory by 1, as this screenshot from the manual published in 1976, I think, will tell you. And there's various different ways that you can refer to the piece of memory that you're going to be incrementing. You can list it here. So you can take a address in 0 page, which is the first 256 bytes of RAM. You can do so with an offset in the X register, or you can do the same thing, but addressing the entire memory. This requires an extra byte of address. But you can only use the X register as the offset. So the NES has 2 different registers for offsetting into arrays, effectively. They're called X and Y. And some instructions allow you to use X and Y, but inc only allows you to use X. So if you accidentally try to use Y as your index, there's no opcode for that instruction. It doesn't exist. And you get a type error if you try to write this code in my Rust DSL. The reason this works is because each instruction, the definition of each instruction in the assembler looks kind of like this. And you can see that the instruction trait is only implemented for the valid addressing modes. So each instruction will define its addressing modes and then implement it. Yeah, only the valid addressing modes are allowed to be the parameter for that instruction. This is a little verbose, and you might have noticed this interpret method here. Like, that sure has no place being in a assembler, and that's because I originally set out to make an NES emulator, which I did, but in the process I kind of accidentally ended up with like 90% of all the pieces you'd need to make an assembler. And I also needed to test my emulator by running little programs that I wrote before I ran it on test suites, because it was only half finished at the time. So I wrote that extra 10% of the code to make it into an assembler too, and that's the only reason I have an assembler. I didn't set out to make this, it just kind of happened by accident, but it's a great accident. It's been so much fun to use to write NES programs. One more little thing that I thought was kind of neat about this is that there's all this ergonomics for writing your assembly. So the inst method that is probably by far the most commonly used method in the assembler, that's you specify an instruction to appear at the next address. You can pass all sorts of different types of arguments depending on what the instruction is. So bytes for immediate instructions that take their argument from the next byte of RAM. Next byte of ROM. Some instructions have no arguments, so you can just pass a unit. You have to pass something because Rust doesn't have function overloading. You can pass it as string, and it'll look it up in a table of addresses that gets generated when you use the label operator. Literal addresses, and this last one is a special kind of label where certain instructions, like the branch instructions, only take a single byte worth of address as their argument, and this is assigned relative offset to the address where the branch appeared, I guess to save memory and to make it take advantage of the fact that most targets of a branch are pretty close to the branch instruction. So you can't branch more than 127 bytes forwards or backwards in the 6502 without going through some indirection first. This is how it's implemented. If people can read, this is, I hope it's not too small. It's not super interesting, but it's all just done with a trait that I implement for each of those addressing mode, each of those argument types. And finally, I've got this real example of an actual function from the program I was showing off at the start. But I'm not going to go into too much detail. I just wanted to show something complete, show that all the this is the function that that asks the controller what its current state is, and in a destructive way, because that's how you do it on the NES, copies the result into a convenient address in like the first page of RAM, so that you can then later refer to it without destroying its value. One interesting thing about this example is that it's got a bunch of named registers. So somewhere in this program, I've got a module that's just a whole bunch of different constants at different, like with different values that are offsets into the into the first page of RAM, so that I can have named variables in my code, which is really convenient. Which brings me to the conclusion of the talk. I've done a fair bit of NES hacking over the years, and you can read more about it on my blog. This is a screenshot from from my NES emulator before it was working properly. It's not supposed to look like that, but here we are. Yeah, thank you for listening.
Can you go to the last slide?
Yeah.
So, like, if I understand correctly, then certain sections of this are like functions, right? If you define the label of the function, then what's happening within that function, like the label.
Yeah, exactly.
Yeah.
So this is the function.
Can you repeat the question?
Oh, yes. Sorry. Complete the question, and then I'll repeat it.
Have you thought about writing a Rust procedural macros that you write it in Rust, and the macro translates it into this?
Right. So the question was, if I had thought about writing a Rust procedural macro that you can that translates to something like this, but allows you to write your functions, your NES functions, in a more ergonomic way. I haven't really put much thought into improving ergonomics further, because I've never really intended on this being like, a thing. Like, it's just kind of happened by accident, and I've just sort of used it whenever I wanted to do an experiment, and added various fixes and improvements as I went, and I've never really had a reason to go super deep. But that'd be cool. Yeah. Uh-huh.
I mean, along those, I was having a similar thought. Would you consider, using the 650 LLVM target for us?
Does that exist? The question was whether I had considered.
I quickly had a look just before I asked that question. Apparently it does.
Whoa.
I don't know if it's a good idea or not.
Yeah, the question was whether I'd considered using the 6502 LLVM target for Rust, so that rather than using a DSL, I could just run my programs in Rust and compile them to binaries that I would run on the net. I don't remember. I do remember reading about Unsafe Rust a long time ago, and it lists a whole bunch of the assumptions that it makes, like that the compiler makes about the hardware that lets it simplify its assumptions. And I forget which one, but I do remember one of them being violated by the 6502, but I forget which one it was. So this is a terrible answer to the question. But yeah, I haven't put a ton of thought into that.
Does it take longer to compile your assembler or assemble the actual program?
Does it take longer to compile the assembler or assemble the actual program? It's significantly faster to run this program than to compile it. Yeah. I mean, okay, it's a pretty simple program, but yeah, running it is instant. Compiling it takes noticeable delay. Running it on the NES is, sorry, yes.
So, what was the first thing you made it work, and how did you feel even?
I mean, the first thing was just like a factorial function, and it still felt pretty good. Like a recursive factorial function to test that the stack worked.
What is factorial?
But like just, implement factorial, like a function that computes the factorial of a number. But the first non-trivial program that I wrote was Conway's Game of Life, which was cool, that felt really good, because there was a lot of complicated things you had to do to make it work fast enough, because you can't just update the display on the NES within a frame. You need like 4 frames. So you can get it faster if you're clever about only updating the things that have changed. And it's the whole deal, but it's really interesting. So that felt really good. Yeah.
Can you tell me a little bit about the UV you get from Zelda?
Yeah, sure. Let me page that back in real quick.
Can you repeat
Let's talk a bit about the undefined behavior in Zelda. I'm going to click on the. Can't click on the link. I'm gonna open my blog in a new tab. This will be aided by a diagram. Let's go to here. Let's go to. It looks like I have more content than I do. I just have several tags on all the posts. Okay, so the thing which is undefined behavior. So the NES, there's a register in the picture processor that lets you control the horizontal and vertical scroll within a 2x2 screen sized sort of virtual screen that you can populate. So when it scrolls like this, that's what it's doing. It's changing this register. But you shouldn't be able to do this kind of thing, where you partially scroll the screen horizontally. There's a way to do it vertically, but if you just read the spec of what all the registers in the picture processor do, there's no way to do what it's doing here. I learned this because when I ran it on my emulator, this didn't happen, and I was like, what's going on? Why is it? I think my emulator did. Maybe I didn't include it, but the point is that I think it would have scrolled the UI off the screen as it scrolled, because all you can do is like set the scroll. You can't say halfway down the screen then set the scroll. But it does say in the manual that it's a bad idea. So rendering on the NES. There's sort of two phases. Time is split up into a period called vertical blinking, and the rest of time. Every 60 times a second, the NES ran at 60 frames a second, which is wild for its age. So every 60 times a second, there's a brief window during which time rendering is taking place, and it is a bad idea to update the scroll register in the picture processor during this period. Doing so can lead to all sorts of weird effects, because the way the picture processor works, like the way it gets data onto the screen, is by setting the current address into video memory that it's looking at, and then reading from that address and getting the tile of that address, and then writing it to whatever hardware goes to the screen. Say, setting the scroll offset has the side effect of setting the current address that the picture processor is looking in RAM. So in RAM, sorry. So, yeah, if you write to the scroll register during rendering, you corrupt the process that it's using to look through memory and take tiles and put them into the screen. But you corrupt it in a way that, if you do it just right, leads to this useful side effect. You can set the address so that halfway through you interrupt the process so that it starts reading from a different place, and then continues to read from that place, and so you end up with this useful horizontal scrolling effect that you shouldn't be able to do. I know it was really fun to discover this, also kind of by accident, when my emulator did the wrong thing and led me to what's actually happening? How does scrolling really work? How do I emulate it so that this undefined behavior has the correct side effect? I say undefined behavior, but the NES was never really officially published. The spec was never officially published, right? It was given to game developers behind closed doors. People reverse engineered it and made a wiki. And when I say undefined behavior, I mean the wiki says you shouldn't do this. But there's another page that says, but if you do, here's what happens, fortunately. So I didn't have to reverse engineer an NES myself.
Awesome. Thank
yeah.
you, gridbugs. It's we have to move on.
Of course. Yeah.